Okay, I think we can start. Um, okay, so welcome to Lab 7. This is on RNN basics. And for till now, we were dealing with MLPs and CNNs, which were really the basics of deep learning. And now we are moving to more exciting things. So in MLPs and CNNs, mostly the data that we were dealing with was unrelated. And now we will be learning how to deal with sequential data. So what do I mean by that is something like audio signals, stock market price, when dealing with grammar, and also dealing with videos where the frames, as you can see here, are related to each other. They come in a sequence. So more examples could be like daily temperature. So the output at one time step is related to the outputs at the previous time steps. So RNNs are designed to handle sequential data, and this can be configured to address various kinds of problems, and we can model these problems in various ways. So I you have already learned this in lecture, so I'll just quickly go through what kinds of problems can be modeled and solved using RNNs. So first would be the very basic feed-forward network. That's an example of which would be image classification, where you just have one input and corresponding to that, you are expected to just predict one output. That is, let's say, a classification task. So it's in this example, if it's a dog or it's not a dog. Another example of a problem that we usually solve is one-to-many. So an example for this is image captioning. We pass in as input just one image, and our output is a sequence of characters or a sequence of words that describe the image. So that's a one-to-many relationship between our input and output. Third, we have sentiment analysis. This is what you guys would be dealing with in today's notebook. So that's an example of a many-to-one problem. You uh, have a sequence of many words or tokens as input and many words as input, which is a sequence of words and they are related to each other. And you just output a one sentiment that is like a positive or a negative movie review in this example. So in many-to-many data modeling, we have two kinds of problems. First can be machine translation. That's like sequence to sequence problems. For example, when here you want to translate a language to another, translate some sentence from one language to another language. So you take as input all the frames at once, and you output all the frames for the translated language as an output. Another example of the same type of problem where you model, where you have many sequences of input and you output many sequences could be object tracking. So here, it's like video analysis. So video is formed with as a collection of different frames. So you are basically taking input many frames and you're outputting many frames, and each frame is connected to each other. Okay, so let's just go through what recurrent neural networks look like. So you can see this figure on the right. The xt is our input at any time step t. A is my network, and not to be confused here, ht is my output and not my hidden state. So that's just like a notation here. So as you can see, there is a loop in this network, And they are basically, RNNs are represented as looping networks. Why is that? Because at I'm using that same network at every time step, and I'm passing some part of my some information about one time step to another time step. So I'm kind of passing the same, uh, looping through the same network, which leads which leads the RNNs to have parameters shared across time steps. So due to this, the derivatives aggregate across all the time steps. And when we backpropagate through time, that you guys must have learned in lecture. So this is how the unrolled network looks like. As you can see, x0, x1, x2 to xt are my inputs at various time steps. And A depicts my network, which is the same network every time. And the relation between the same network is what was represented as a loop in my diagram. And H0 to HT again here, not to be confused with the hidden state that we talk about in RNNs. It's just an output here. So just so we can relate to the diagram we used in lecture. So this is what uh, you guys use in lecture. This depicts the unrolled network, and as you can see, x0 to xt are my inputs, y0 to yt is the output, and this is my hidden layer. So it's no fun without any math. So we have the descriptions about the three kinds of weights that we deal with in RNNs, and yeah, you guys can go through this. This is just a slide from the lecture. Okay, I hope everyone is following. Is there any doubt? Yeah. So let's take a slight detour. Let's think about how does my network even know that it is a text input. So when dealing with RNNs, a lot of our problems we solve are related to text. So it's important to know how to represent text. So one very simple way to represent text is one hot encoding. For example, here, like you can ignore these graphs for a bit. So in this example, never gonna give you up. And these curly braces represent my vocabulary size, which is 5. And to represent a word in this, in the way we call one hot encoding, would be this vector, which represents never. So if you have to represent all the words, each word in the vocabulary, you can just guess how much, you can calculate how inefficient it would be to use the whole vector just to represent one word. So we have something more efficient, which makes us use the space better. And that's called having a input post-processing, the post-processing on an input, and putting all the words in a word embedding space. So this is an example in the graph, as you can see. These representations are mostly what the latest architectures use. So we basically put our word in a two-dimensional space where it is represented as a vector, and the vectors, the words that are somewhat related to each other. For example, here, we can say niece, sister, aunt. They have some relationship between them, and they are nearer to each other in this word embedding space. So the output for our model would be a probability distribution. So as we are talking about, I'll just go back. So for here, for example, here in the sentiment analysis problem, we are talking about the output at each time step, or maybe we can think about many to many sequence prediction tasks. So at each time step, I am expected to output a probability distribution. So for example, when I have a sequence of never gonna give you, and I'm expected to predict the fifth word, I want to output something like this PW, which is a probability distribution of all the vocabulary at that point. And as the vocabulary keeps on increasing, our probability distribution keeps on increasing. The length of the output keeps on increasing, sorry. Okay, so let's see how RNNs work as an example of a prediction task. So here, the problem that we're dealing with is never gonna give you. We are given with this sequence of words, and we want to predict what comes next. So in this network, the input at the first time step for me is never. And my intermediate output for this particular network for this time step would be the probability of word one given that the previous word was never and a hidden state. So this output now goes to the second time step. So I have at second time step, I have my second word as an input, and I also have the output of my previous time step. Please note that this gray square, this is like the same network. So I'm just passing the information across time. Similarly, my output here is expected to give me a probability of W2 given my H1, which came from the previous time step, and the current input. Moving on, so on and so forth. So I'll finally get my probability of H5. H4, sorry. So just a question for you guys. What do you think is H0 here? Okay, can I get some thumbs up if people are following? If anybody would like to answer what H0 is in this network, which I call my hidden state at 0th timestamp. Okay, let's move on. So till now, we covered how my RNNs look like and how the unrolled network looks like, how do we represent text. And this is a simple example of how we model a prediction task using RNNs. So this is how the gradients would be backpropagated. As you can see, we cannot backpropagate through one time step independently, and to calculate my gradients at time step 2, I have to know the gradients at time step 3. So that's why we call it backpropagation through time. And after many iterations, RNNs go with a problem called short-term memory and vanishing gradients. So why do RNNs suffer with the problem of short-term memory? This is because after many iterations, we are maintaining the same hidden state, and we are updating the hidden state at every time step. And after many iterations, it has a lot more chance that it forgets what it learned for the initial few tokens or initial few inputs. So that's why it suffers from short term memory and vanishing gradients. You would be learning about this in detail in lectures. So we deal with this using architectural solutions like LSTMs and GRUs. So you guys would be working on LSTMs and GRUs in detail in homework 3. And yeah, you'll get to learn a lot more about it tomorrow as well in the homework 3 bootcamp. So yeah, uh, RNNs, understanding RNNs is important because it also leads to better solutions than LSTMs and GRUs, and it finally leads us to attention. So yeah, get excited. And here is the task for today. We would be dealing with sentiment analysis, and I hope everyone can download the notebook. We would be tracking your checkpoints on Piazza. And yeah, I'll hand over to Ritvik.
Uh, okay. Do you have it open or it's like notebook? Okay, just click this. Okay, everyone. So today we will do sentiment analysis, and for that, I have provided like a guideline of what is the expected outputs. We have around three checkpoints. I think we have four checkpoints. So you can go through the code and try doing it. I will start with the checkpoint one. So let me give you a little bit of background on what is the data set and what are we actually going to do. So sentiment analysis is like uh, on social media platforms like YouTube or Facebook, you see like the video or the content that is given, and sometimes we need these companies to understand like if the content that is posted is like a positive, negative, or harmful, hateful, like so that they can do content moderating. And in short, we are trying to do here is to understand if the text that we have been given is positive or negative. Okay, and for that we will be using an LSTM, which is provided by PyTorch LSTM module. So let me start by loading the data and visualizing it. By the time it's connecting, we can move to the next cells. Uh, so here is the reviews.txt, which will be the all the training data, and the labels.txt, which will be having uh, the y value. Like this is the x and this is the y that we provide to the LSTM module. So the first will be we see the reviews, like the first 2,000 words that are given, and it's like a bunch of strings that we have been provided, and the labels will be positive or negative. The important thing you have to do for data pre-processing is that uh, these words, each of the word is like concatenated, so they have provided one giant string, but the individual reviews are separated by /n. So what you should do is first convert all the reviews to lowercase, and then you need to remove the special characters which are provided by the punctuation library. Once you do that, you can split uh, the remaining data by slash n, and you need to create a dictionary of indices, which for each word you need to provide an index, because we don't pass actual word to the LSTM model, we provide an embedding. So this is like a simple embedding that we are providing, which is like a dictionary. And make sure to use the dictionary from 1, because later we will see why are we reserving 0. So I will give around, let's say, 10 minutes for solving this. After that, I will try coding it in front of you. Um, if you have any questions, you can ask on the Zoom, or yeah, you can type in the chat as well. So once you do all this, you will be seeing the number of unique words, which are going to be around 740, 72. So let me pull up these slides while you try to solve the notebook. The expected output for the first checkpoint is going to be these three. Uh, the number of unique words, a test set of words which are shown here. So the text, a text review and the encoded reviews you can see, and then a histogram of the distribution of the words. So this will be important because you can see that there are certain words or certain text which are of length 0, and it will be helpful to remove them because they are not providing any information. Also, there are words going till 300, and for LSTMs or any amount of any models, we like to provide them a standard set of input, and so the text here has variable length, and that's why we need to pad them further. So at 8:30, I will start coding, and by the time you can start on your own, and you can message if you have any problems in doing. I can do that. That's yep. This is the you can go to the post number 956 on Piazza, which is providing the RNN basics, and the notebook you can download it from there and complete the checkpoints as well. All right, guys. Hope you have some progress. I will start doing here on myself. All right. Okay, one second. All right, there was some technical glitch. Uh, Somehow it got solved. That has never happened before. So, but we will solve it again. Right. Let's hope it's solved. Okay. Yeah, we have the link now. So it's okay. Yep. Okay. Alright, so what we did in the first two code blocks is that I converted all the reviews to a lower, uh, you can say a lower case words, and then I joined all of those words, uh, comparing if that each of the word is not in the punctuation library that we see here. Once I do that, as we know that the all the each of the review is separated by slash n, so I'm splitting all the text with respect to slash n, also the labels because those are also separated. So now I will create a vocabulary library. Okay. Uh, so once we split each of the review, so once we do that, we will have a list of all the reviews that we want in a order. Correspondingly, we have their labels. Now, the issue is that we need a vocabulary. How do we do that? So we can do is join all these lists together, and then we are splitting them again. But the main difference here is that previously uh, all the text had slash n, and we don't want slash n to come into our vocabulary if it is not a proper textual word that we see in the text. So that's why we first split it with slash n, then we are joining it again, and then we are splitting again. Next, once we have all the list of words that are occurring in the these reviews, what we need is actually a count of all the words. Okay, so for it's simply done by uh, using the counter library from collections module, and we will sort the vocabulary. So we are passing the counts that we have, which is a dictionary of. Let me can do it here. So it will be a dictionary of the word and the occurrence of the number of occurrence of the word. All right, and so you can check the sorted uh, like documentation for the sorted function. And what we need here is that we have the dictionary already, but we want the number of uh, like the number of occurrences that are in the word because we need to see the histogram of words. So the key will be so dot get is a special function in library, special function for dictionaries where uh, it can get the default value or it can get the actual value that we want from the dictionary. And I will just do reverse equals true, even though it's not completely not necessary for the year. It's like optional if you want it in reverse order. So now, now here we will create our a vocabulary to integer dictionary. And so so uh, word will be the actual word, like the unique word that we see, and I will be the number of occurrences of the word. Sorry, I will be the index of the word. So, and remember, we need the index to start from one. So I can handle that with a special command. So enumerate has a special function which is the start. So for start, we'll provide one, and we are trying to enumerate uh, the vocab that we have. All right. So as you can see, the number of unique words we found are equal to the expected number of words, which is 740, 72. Yeah. So now, once we have this dictionary, we can just remove the words and put in their indexes in place. Uh, yeah, please turn off your generative AI recommendations. I will just turn it off here for now. Okay. Okay, so I can explain the review split. This will have uh, all the sentences of reviews, but the reviews will be text right now, and we need to convert this text to integer. So I'm doing using a list comprehension here and getting each review. And once we have the review, I will split the review and I will pass that each of the word to my vocabulary to integer dictionary, and I will just append it to review integers. All right. For visualization, I will I will write the reviews and the encoded value which will be the review integers. All right. As you can see, can compare it with the expected output. Yeah, I think it's matching. Uh, okay. Moving on, we will do the similar thing for the labels. So we want the positives to become 1 and the negatives to become 0. This will be like a simple statement where if you can use if positive, then it is 1, else it becomes 0. Um, yep. So we have encoded our labels here, and we have the histogram of words. Let me repeat what I said when we saw the histogram first time. The thing that we want to see here is the frequency and the length of the words. So we have a frequency of around 1000. Like there are 1000 reviews which are of length 0 and 100. But the thing is, we are not sure which are of length 0. So we do not want any reviews which are of length equals 0, because that will be not a positive or negative sentiment. Also, we don't want uh, any number of reviews to exceed a particular length. And the length that we prefer here is going to be 200 words. I know it's very less amount of words, but currently we are using LSTMs. And for more number of words, we do more powerful architectures that we see later. So here I have created a list of indices that do not have a length of review which is equal to 0. Uh, the reason I have created it in the form of indices is because once we have this all the each of the indices that are not having a review length of 0, we can use those indices to get the reviews as well as the encoded labels. So review integers, we just take the indices here, and similarly we can do it for the encoded labels. All right, we removed one review which is of exactly 0 length, and now we can truncate all the reviews to 200 length. All right, I have completed the checkpoint 1. Uh, I will immediately start with checkpoint 2 because we are running out of time. Also, uh, this was like enough time for you to uh, start on that. Okay. So our training data will be the review integers, and we will going to trim them according to the split index. Similarly, the training wire will be the encoded labels, and similarly we'll be trimming them. Once we have our training data, what we need to do is split the remaining data into a subset of test data and validation data, which will be like 0.5 of the total of remaining data. Okay, let me debug the issue. Okay, so Python is a bit tricky. I forgot to put curly brackets here, and yeah, because it's a list comprehension, so turns out it's another issue. Um, all right, I will have to take some time in debugging it. Um, Okay. For now, like, can move on, but so this shows kind of incorrect. It was previously one, uh, but yeah, we will move on to the next part for now. So this will produce the validation X and the test X, and now we can do the pairing. So yeah, I will start do the coding here, but you can try on your own, and like we can also post on Piazza like what like code, like did you find any bug that I was doing? It might be hidden in somewhere here. Uh, so here for pairing the batch, you can use the pair sequence function that is provided by PyTorch, and you can pass in the list of reviews and make batch first equals true. Alright, so that will provide the padded batch, and similarly you can see the padded batch dot shape, and this will also be done in the data set class. Uh, so so the expected outputs here for the number of reviews is 20,000. Validation set is 2,500 and the test set is 2,500. Uh, for the tensor, like the padded tensor here, the padded batch, it will look something like this. Uh, this one. Moving on to the data loader, let us do that. So yeah, this provided part is already correct. Don't need to make any changes there, but you can make changes here, which is to initialize the dataset class. So that would be reviews dataset that we have here, and we will pass the review, which is the train X, and the train Y. And similarly for validation data set, we will be again initializing the review dataset class and passing in the validation X and the validation Y. Okay. For the test dataset, again similarly we will again initialize the dataset and we'll pass in the test X and the test Y. All right. For the train loader, we will use the data loader that is provided by PyTorch. Uh, so we'll pass in the training data, and we can, it's preferable to do shuffle equals true, since while training we don't want the model to look at the the text in the same order, because as we have seen in the lectures that the gradients could be like moving in like a circle or a U shape, and they won't uh, they might never converge to the local minima. Let's do the batch size equals to the batch size we have, and the collate function will be the collate. Uh, will be the collate function we have defined here, which is accessible via train data dot collate function. All right. I think this will be very similar for all the other loaders. So we'll okay. So instead of train data, we will have our valid data, and for here we don't actually need shuffle equals true. I will prefer to use false. Batch size is same, and so is the collate function. So this will be similar for the test data as well. And similarly, shuffle is not required here. Uh, Once you run this cell, you will see an output which is like this. So batch size of 256, training data samples, which is of 2000, batch is 79. Uh, so moving on to the next question, which is going to be obtaining one batch of training data. So, so I think we have provided the code already here. You can just run it. Coming to the sentiment analysis, that the main part that we want to actually learn here. Uh, so as we have created the embedding layer because we don't want to pass in the text to the model. So this is gonna check for if you have a CUDA device available. This is the sentiment network. So let me quickly code this up. For the embedding layer, we have PyTorch embedding layer that we will use here. The number of embeddings will be equal to the vocab size that we created, and the embedding dimension will be the one that we initialize the class with. Uh, PyTorch provides us with nn.lstm, which is inherently going to do all the sequential, you can say sequence of words will be given to it, and it will do the looping automatically. PyTorch also has another LSTM network, so that is called LSTM cell, and you can manually implement the recurrence there. But here we will prefer to do it automatically. The input size will be equal to the embedding dimension. Hidden size will be equal to the hidden dimension. The number of layers, that will be equal to the n layers we have. Bias, uh, we don't actually require bias here, so let's skip that. Um, we can add is dropout. So we can do dropout equals to the dropout probability that we have, and we can do batch first equals to also another feature that LSTM has in PyTorch is that we can make it bidirectional, which will make it even better. So this is all covered in lectures. Uh, we will just see how to implement them here, and we need our FC layer. So once the LSTM layer gives the output, we need to convert that output into either a 0 or a 1. So for that we need a linear layer of output size equals to. The input dimension to the linear will be 2 times the hidden size. Uh, I hope this is covered, uh, like you understood when this was covered in the lectures. So we have our indices, which are the text that we converted to numbers. Now we will pass these numbers to embeddings. Now you might wonder, like, why do we pass them to the embeddings since we already have them as numbers? This is because the numbers that we have created the vocabulary based on the occurrence of the word, and we want the embeddings to hold certain information regarding these words. Like if the two words are similar, then they should be closer in the embeddings, and if the two words are far, then they should be further apart in the embeddings. We pass our input x, and then we pass the embedding to our LSTM. All right. Once we get the output, we pass that output to our FC layer. And remember, we only require the output of the last layer, but that is already taken care by PyTorch. But if you are doing the LSTM cell, you need to take care to only take the output of the last uh, LSTM output. All right. So here we will return the output of the last time step, which will be the out. All right. So once we do that, we initialize the network here. The model, it will be sentiment network, and we will pass in all the values that we see here, which is the vocab size. All right, we have defined our model. Now to train the model, uh, we will define our loss function. So as usual, we will use our cross entropy loss. I hope you guys understood what actually happens in the cross entropy loss, since this was covered in homework 2. I will use my favorite optimizer, which is the AdamW. We'll pass in the model parameters, the learning rate, and the weight decay. For schedulers, there is you can choose any of your favorite schedulers, but I will go with cosine annealing one. All right. So once we define it, we have the scalar. We run this model. We have the default like default code that is provided for training the model and validation of the model. Please go through the code. This will be helpful for your next homeworks too. And once we start training the model, we will expect to see and our so this will be the network. It will be having an embedding like input dimension. The LSTM cell will be uh, this like bidirectional to drop out and the linear layer. And once we start the training, the epoch 1 to 20, it should look around like with a learning rate of 0.001, a loss of point validation loss will be 0.69. But after you train it for like 20 epochs, you will see the loss decrease by a little bit. So the model has learned a little bit of information that we want it to. So all right, we only have 10 minutes, so I will start with the checkpoint 4 as well. Uh, so the expected output will be the test accuracy and the test loss. So this code is already provided. No need to make changes here, but we can do is do the clean and encode review. So we didn't do this for the test reviews, which is like this message. So we will have to do the pre-processing again that we did before for the training data. All right, we have that. Now the textual words will be just splitting the text. All right, and once we do that, we need to append to test integers. So again, we need to take into account that we have a maximum length provided. So all we need to do is once we get the vocab to integer, we can just slice it. Okay, so once we do that, we will see. Okay, yeah, I didn't provide the output, but yeah, you will see a list of integers that will be just encoding of this, and then we will pass the words to the our prediction model, and that will uh, let's do that. So so okay, we'll pass the tensor, which is the tensor of the test integers. Oh, we have to do that part. So it's just calling the function and passing in the test review, the one that we have here. All right. Now we have the test integers review. We pass in that to the like that to the tensor, and we pass that to the device. So we need to pass the tensor. That will be done by device. Okay, and the prediction will be the output, but we need to. It will be like 0 or 1. So we need to convert that into. So we will convert the 0 or 1 into the appropriate word, which is positive or negative. And since it will be a tensor of uh, like a large size, we will have to argmax it. So get the maximum argument for that. All right. So this will give us the prediction that it is classified as negative. Similarly, we will do it for the rest of the list. Uh, so this will be just as calling the function and encoding it. And similarly, we will do this part for the next section. All right, and then you will see that the review will be classified as positive. We're done. All right, we will release the completed notebook in on Piazza in a couple of hours, and I will give it back to Ishita.
Okay, thanks Ritvik for going through the all the coding part for the sentiment analysis problem. As we are out of time, we would be taking up questions on Piazza. If there's